Hi, thanks for joining me. Today I thought I'd go over one of the fundamental theorems of calculus, and that is that the derivative is kind of like the inverse of the integral. But let's make that a little bit rigorous. If we have a function from the reals to the reals, which is bounded and continuous, and I'm calling this function f, then d dx of the integral from 0 to x of f of t dt is equal to f of x. Let's get stuck into the classic proof. Okay, so let's start from the left-hand side, d dx of the integral from 0 to x of f of t dt. Now we're going to use our limit definition of the derivative, but firstly notice that this guy inside the brackets is just a function of x, so we'll call it g of x, and our goal is to work out g prime of x. So this guy here, just by definition, is the limit as h goes to 0 of g of x plus h minus g of x all over h, like so. But then just using the definition of g of x, this is equal to the limit as h goes to 0 of g of x plus h, which is just when we plug in x plus h into this guy here, so 0 to x plus h of f of t dt, then minus the integral, or g of x, which is just the integral from 0 to x of f of t dt, and then of course divide through by h. My pen is about to run out, sorry. And on the top we've got an integral minus another integral, but notice this is from 0 to x plus h, and this is from 0 to x, so this thing here is kind of cancelling all the work between 0 and x here. So the top actually just becomes the limit as h goes to 0 of the integral from x to x plus h of f of t dt, all divided by h. Now I'm going to skip a bit of the rigor here because, you know, if you've kind of done any kind of real analysis before on differentiability and continuous functions and boundedness and things like this, you can make this slightly more rigorous. But for those of you that haven't seen that sort of stuff, let's just have a look at the top, what we have here. Everything so far up to here has been rigorous, but look at the top here. We've got the integral from x to x plus h of f of t dt. Now f is a well-behaved function. It's continuous and bounded, and in particular it's continuous and bounded near x. Okay, but we're taking h going to 0. So all values in this very small range, x to x plus h, that f evaluated at them are going to be very, very close to f of x. So this f of t we can kind of approximate with an f of x. So if I just swap the t now, there's f of t now to an f of x, and now f of x is a constant. X is a constant in this case, even though we are taking the derivative with respect to it. With respect to h and t, f of x is a constant, and in particular with respect to t, so we can bring it out of the integral, like so. I forgot to put the h in the denominator. So we have f of x times integral from x to x plus h of just 1 dt, but that of course is just x plus h minus x, which of course is just h. So we've got f of x times h divided by h, and of course we're taking the limit as h goes to 0 still. So perhaps I'll put approximately equals to the limit as h goes to 0, but of course these h's cancel, and what we're left with is just f of x, like so. Okay, and that kind of semi-proves what we wanted to show, and I guess to prove it in rigor, you kind of got to make this guy rigorous, but certainly it is, but to make it rigorous, you have to use a bit of knowledge about bounded functions and continuous functions, but I'm going to assume that not all viewers will have that, so I'm just going to kind of put my approximately equal to there and call it a day. Anyway, I hope you have enjoyed this quick video. Pretty much a full proof, but you know, apart from this small approximately equal to, we're pretty much a full proof to one of the fundamental theorems of calculus. And now most of these kind of fundamental theorems of something in maths generally have quite difficult proofs. If you look, for example, at the fundamental theorem of, is it algebra? I think that's what it's called. I was going to call it the fundamental theorem of complex analysis, but that's not true. But the one that says that every polynomial has of degree n has n roots in the complex plane. To prove that is actually quite difficult, and you need to use high-level complex analysis. But something like this is actually not too difficult to convince yourself is true. Anyway, I'm waffling now. I want to thank you for watching. I'll catch you in the next one. Have a great day.